Hello everybody, my name is Darina Štyriaková. I am from Slovakia and I am very happy that I can be part of this year the ESEE mining school. I would like to tell you something about innovative bioprocessing of raw materials. But first I will introduce you my company, startup, Ecolife. We are first and leading provider of new ecological bio-leaching method for ecological release of elements and degradation of organics, which solves environmental hazards and makes mining industry greener. But I will tell also a few words about support of EIT raw materials, because we would be not here where we currently are. So all started with business idea competition 2 years ago when we won third prize in grand final in Budapest. We are also part of EIT Raw Materials Accelerator program. Now we are in phase 3 with 4 another teams from the Europe. I was coordinator of EIT Raw Materials funded project BioLeach, which was focused on innovative biotreatment of raw materials. There was a lot of different universities, research centers and industry from all over Europe. And we have been invited to present this new technology to many conferences, and biggest one was PDAC in Canada this year, or a Raw Materials Summit in Berlin. I have been presenting also in biggest Green Expo in Rimini in Italy. And something from my background, I am coming from scientific and academic field. I studied geology in mining faculty, and I made my PhD in biotechnologies in Slovak Academy of Sciences. But then I decided that this great technology cannot stay just somewhere in laboratories, but I need to put it into the real world. So that's why I am having this startup and fighting already second year. And this is really far away from scientific world and academic world, because there are many challenges, like how to manage team, how to create contracts, how to negotiate price with customers, and so on. So it's difficult road, but I am very happy about this, and we are now having contracts with global players on the market, so everything looks very promising that we will somehow achieve and bring this great technology to the market and to the world. Okay, but I will start with this why we are doing this, what we are doing. Because it could seem that European Union is running out of resources, and raw materials mining in Europe is decreasing every day, and raw materials production is decreasing every day. And on the other hand, our consumption is growing. But we have high potential. We have high potential which is hidden, and it's represented by first one, industrial minerals, which are non-exploited, or they are wasted for low value purposes because they contain impurities in form of metals. And because of this, they are used just for such construction purposes and really low value purposes. And then we have to import these high quality raw materials. Also potential lies in metallic raw materials, in primary metallic raw materials, which are including low-grade ores, because there is no economical technology to extract metals from these low-grade ores. And then very important potential what we have is hidden in waste, in mining waste, in industrial waste, and also contaminated environment by heavy metals. So today problems in raw materials are that industrial minerals are in low quality because of metallic impurities, and that's why they are wasted. Then we have industrial waste, and this industrial waste is deposited on high costs, up to 80 euro, for example, used foundry sand, or even contaminated soil is deposited on up to 200 euro per ton. And this all because this waste contain heavy metals. Then mining waste and contaminated environment also represent high risk for our health because of this heavy metals content. And on the other hand, as I mentioned, demand for raw materials increases, which leads into import and high CO2 emissions and high transportation costs. So such example on climate impact of this long distance transport. It's not just high costs, but really the CO2 emissions are enormous. One truck is producing 3 kilograms per kilometer. So if we take example of middle-sized glass company, they need 45,000 tons of high purity silica sand, which is their main material for glass production, which means a lot of material which have to be transported. And usually they are transporting this material on more than 400 kilometers distance. If we would create local resource for just this one glass company, this would mean that we would save 3,000 tons of CO2 per year. So we are trying to make local resources attractive alternative. Okay, here is a picture of this vicious circle. So high quality and high purity raw materials are imported, which means high transportation costs also, except the CO2 emissions. And on the other hand, there is a lot of low quality deposits everywhere. Everywhere around us there are some deposits which could supply the raw material, but they cannot because this material is in low quality because of these metallic impurities. And I will continue with importance of these industrial minerals, because everybody knows critical raw materials. Here is this well-known picture of critical raw materials and their supply risk and economic importance. And you can see that there are feldspar, kaolin, bentonite, silica sand, magnesite, many industrial minerals. And when you look on gold, they have even higher economic importance and supply risk than gold. So they are very important for our economy. And these industrial minerals can be gained from local resources which are currently in low quality, but can be improved. And I will continue with such a very basic example with basic and most common raw material, which is sand. You can think that sand is everywhere, that sand is in the lowlands, on the deserts, on the beaches, everywhere around us. So how can be sand critical raw material? But demand rises rapidly, from 7 to almost 20-30 billion tons. And also there is, you will find endless number of articles about sand crisis, and resources of this high purity and high quality sand, this white sand for glass industry or ceramic or paintings, whatever. There is estimation that there is last 20 years of supply of this high quality silica sand. And in Europe, we have more than 100 silica sand deposits currently operating, but only few of them are in high quality. And these deposits then have to transport their raw material on very long distances. And problem is that all of these 100 deposits in Europe contain metallic impurities. So what we do? We turn low quality industrial raw materials like silica sand, but many others, into high quality and high purity raw materials. And by this, we increase its availability, but also the value from a few euros to even 1,500 euro per ton. And this we do by biologing, by heterotrophic bacteria, which dissolve metals and remove metals. This is innovative solution and highly efficient solution. It's fully biological and non-toxic, and it's economical and zero waste. We can extract almost all metals, including rare earth elements, and our byproduct is organic biofertilizer. The efficiency is same, like in when you use very dangerous and strong acids, like they are using in few cases. One case is in Norway, and they are transporting silica sand even from America, treating it with hydrochloric acid, which is very dangerous, doing flotation, which means next chemicals, so it's very expensive process. But this sand is for high applications, so it's very expensive then after this treatment. But we are now cooperating with them and trying to replace this dangerous hydrochloric acid leaching. And we have also very wide application, because this bioleaching can be applied to carbonates, hydroxides, oxides, silicates. So the application is very wide. Okay, and here you see detail of grain, of quartz grain. And you see bacterial adhesion on this quartz grain, where metallic impurities, you see them, this orange iron on this grain, they are covering or they are impregnated on the surface, in every grain. So that's why these metallic impurities represent problem for every conventional separation method. You cannot use gravity or magnetic separation to remove these metals away because they are covering the surface. So only one solution is use strong acids, which are very dangerous. But as you see, this is a picture from real experiment, how these metallic impurities are disappearing in bioleaching process. Also, effect of bioleaching is on surface of this mineral grain, because these bacteria are attacking this surface. So this surface is not anymore smooth, which is a problem in desert sand. Because yes, in desert we have a lot of sand, but this sand cannot be used in construction because of the smooth surface. So it's not suitable for construction products, but the smooth surface is destroyed in bioleaching process. So that means that this sand should be again usable in construction, even from deserts where are huge resources, and this could solve this global sand crisis. And also, this sand in deserts, it's brown. And it's brown because of these metallic impurities. But we can remove these metallic impurities and make this sand usable even for glass industry. Okay, and I want to say that this process, this is nothing dangerous, nothing hazardous. This is just inspired by nature. It's a natural process, which is normally even happening in the nature. And on the right side, you see such controlled bioleaching process in the middle, and this gradual metallic impurities removal in this middle layer there are metallic impurities, but up and down there are not anymore. And yeah, these bubbles there, this is because there are these bacteria, they are living and they are breathing. And here you see example of our operation in thermite deposit, where we improved quality and value from 20 to 55 euro per ton, and this is how it looks like. We operate in basins or in tanks, or we can also operate on the heaps. Here is one video from our operation. This is silica sand before bioleaching, this brown, and you see in this basin, the full basin of this white sand, which is already after our process. It's clean, and all iron was dissolved into the leaching. Okay, here is picture how we produce this 300 tons of high purity and high quality silica sand. For near glass manufacture, for white glass production. Okay, and another example, another video, how looks like this sand before treatment. This brown sand which you usually see even on the beach, and we can create from this brown sand such nice, beautiful white sand by this metallic impurities removal. And volume which we can treat is unlimited. Okay, and few more examples. On purification of raw materials by bioleaching process. Here you see improvement of silica sand from Slovakia. And another example, here is silica sand from Romania. And we worked also on it was even not silica sand, but it was just sand from Croatia. And actually in Croatia, it's a big problem with sand. Even your biggest glass producer in region is importing on more than 600 kilometers distance, which means a lot of CO2 and big transportation costs. But we can improve your local sand for green glass production, at least. Then we worked also on pebble from Slovenia, which is for this deposit currently waste. They are not doing nothing with this material, but after iron removal, this can be used for glass production. And we can work not only on this quartz material, but we are working on many others, like here you see improvement of kaolin, which is important material for ceramic, for cosmetic, many different industries. And it's also in a lot of cases, it's contaminated by metals. Or another raw material, bentonite. But we can work on, currently we are working also on zeolites because we need to improve whiteness for one customer. Then we are having already contracts with really global players, but I cannot mention their names because we have NDA, but we are working on materials like mica for painting industry to improve color of this mica. We are working on talc. We are working on different kaolins, on diatomites, dolomites, magnesites, so many different industrial minerals. There always is problem with metallic impurities. Even now we have request on spodumene, which is lithium material, but it's also problem with iron there. Lithium should stay, but this material or this mineral will be used for specialty glass production. And also the problem is iron. Okay, and as I said, we operate in the basins, but we can also operate on the heaps, which you see there. And regarding this liquid residue, what you see, where are these metals dissolved. This can be, or these metals can be recovered, like iron can be then used in steel production, but in many cases we are keeping it inside because it's very important macro element in our organic biofertilizer, because our residue from this process is suitable for agriculture, and yeah, it's organic biofertilizer. Also, these microorganisms or heterotrophic bacteria are producing organic acids. These organic acids are oxalic, pyruvic, butyric, malic, citric, different acids which are in our bodies, in fruits, wherever in nature, so they are totally not dangerous. But they have new application in agriculture. They are very promising replacement of pesticides. And the science is looking for some industrial process which will produce these organic acids, but currently there is nothing. We are first one industrial process which could produce these organic acids, and they can replace this hazard of pesticides. So I will continue with problems of these pesticides and chemical fertilizers. Because the soil, in case we are using these chemical fertilizers, the soil is degraded, and also microorganisms which are there are killed. Most of them are killed because of these chemicals. And then this leads to this, that plants are unhealthy and they are weak. They're having not enough micronutrients and macronutrients just from these chemical fertilizers, which are even going into underground water. And this all leads into increased usage of pesticides. And then our food and water is contaminated. There is new study which shows that already 85% of our food is already contaminated and have residues of pesticides. And yeah, already in our bread because of flour, and also a lot of animals like bees are killed because of these chemicals in agriculture. But chemical or organic fertilizers and biofertilizers are very expensive. So farmers are not using them. So solution for this problem in agriculture can be our residue or organic biofertilizer from our bio-leaching process. It's very economical solution for farmers because it contains these micro and macronutrients dissolved from these natural minerals. Like, for example, in silica sand, there is impurity like mica, feldspar, which will be dissolved. And there is coming potassium and calcium and all these elements from these dissolved minerals. Also, this iron is very important macro element, very important in agriculture. Or magnesium is currently missing in soils. And except this bacteria, they are producing these organic metabolites, and these organic metabolites, they have pesticide effect. So by this, we are decreasing need for pesticides. And by this fertilizer, we are renewing these killed microorganisms. We are renewing the soil microflora because there are still some bacteria living, and they are very beneficial because these bacteria, they can increase soil health and fertility, and also increase crops growth rate and yield, and also increase immunity of crops to diseases. Okay, so here is example which I mentioned, that at Termi deposit we increased quality and value of this raw material from 20 to 55 euro per ton. But at the same time, we produce this organic biofertilizer which have value up to 80 euro per cubic meter. And in this specific case, there is demand 45,000 tons per year for this high purity and high quality silica sand, which will produce 90,000 cubic meters of this organic biofertilizer. Here is one photo of our operation in basin. This is this production and of this biofertilizer and the treatment of raw material at the same time. You see that you can put hand in, it's really nothing dangerous like in case of autotrophic bioleaching. This I will explain later because there are two different ways of bioleaching, and one is quite hazardous and our is quite environmental, but this I will explain a little later. Here is video of this process, how it look like in real. You see this bubbling, and this bubbling is there because these bacteria are living there, working there and breathing. So this is how it looks like this process. They are working there and doing these bubbles in the sand and removing all these metals to this residue, to this leachate, which then contain all these dissolved minerals, and it's valuable fertilizer. Okay, and also by this technology, we can replace dangerous mining techniques. Here you see Rosia Montana open pit mine in Romania. Plant renewal here should be done by gold cyanidation mining technique. If approved, this would become Europe's largest open pit gold mine. But local authorities do not want to allow such operation. And I will show you why. But this dangerous mining technique can be replaced, as you see in this picture from scanning electron microscopy. This can be replaced by our ecological technology because bacteria, they're attacking the silicate matrix, this rock matrix, and extract metals. And here is how it looked like after a past operation by the cyanidation mining technique. There was accident, and whole village is now under this tailing waste. You see this acid is everywhere, and whole area is really toxic. Here is river, which is in the village, few kilometers away, but it's totally orange, and it's because it's contain a lot of heavy metals. So because of this mining there, the whole area is heavily contaminated, and that's why are people scared from mining activities. And it's hard to get permissions to make new minings, and yeah, whole mining is usually like some kind of something negative for the people. And I will continue with bioleaching by autotrophic bacteria, because usually for mining, there is way how to do it by bioleaching. You maybe even heard something about bioleaching, but there are two different ways. This first way, which is already used in many places in the world, and we have also operation in Talvivaara mine in Finland, where they are doing bioleaching by this autotrophic and acidophilic heterotrophic bacteria. They are getting nickel, but it's very dangerous. They had already big environmental problems. You see report from internet, because in this process of autotrophic bioleaching, they are calling it classical autotrophic bioleaching, there is decomposition of sulfite ore. And these bacteria, they are getting energy for their life from decomposition of the sulfite ore, but the result is creation of sulfuric acid. by these metals are extracted. This is very cheap process because yes, this is also natural process which is happening in the nature. That's why we have acid main drainage because of this process. So it's economical because you are using the microorganisms which are working, but it's very dangerous because there is this sulfuric acid. But there is way. I have here one video which is created by BRGM and EIT raw materials about biology.
Increasing amount of minerals in everyday life, but mineral resources are not inexhaustible. When we extract metals from underground deposits, many are left behind, as the remaining elements are not valuable enough to extract. This is known as mineral processing waste. To extract valuable metals from mineral processing waste, scientists began to study a natural phenomenon: bioleaching. Let's see how it works. Mineral processing waste contains minerals, but also living bacteria.
We bacteria can thrive in these piles of waste. All we need is access to air and water to multiply. But we also need energy, which we can collect by dissolving and transforming metals. This is bioleaching. In the process, we release acids that can corrode soils and cause environmental damage. To scale this process up for our needs, the scientists came up with a process to boost our metal production. To do this, the mineral matter we live in is ground into a powder and plunged into a bioreactor, a large and continuously stirred tank with water and nutrients. In this environment, we can thrive and multiply exponentially. The result is a solution that contains the metals originally contained in the mining waste. Then, all that's left to do is chemically filter the solution to retrieve the metals in solid form. This process also has the benefit of keeping the sulfuric acid we produce within the lab or factory. Otherwise, it may leach into the soil. The bioleaching process has moved beyond research and is now applied in the field. Bioleaching produces 5% of all gold and 20 to 25% of all copper extracted today. And research is still underway to find methods of applying this process to other waste, such as circuit boards, for example. In this manner, scientists have found new methods that protect the environment and reduce waste by extracting the most value from it.
Okay, so this was a very nice video about bioleaching and how it works. And there was explained that yes, it's really good mining method and probably the best one how to extract metals from sulfate ores. But we have to be careful because of this sulfuric acid. But there is possible also combination of this autotrophic and heterotrophic leaching. And difference between this autotrophic leaching, which I already explained, which is creation of sulfuric acid and decomposition of sulfidors, heterotrophic bacteria and microorganisms, they are taking energy from degradation of organic. It can be they are living from some organic source. So we have to feed them with organic, or they are having already some oil pollution or something like this. This can be also food for them. And by this process, the oil is totally degraded. Yeah, from this heterotrophic bioleaching, as I mentioned, there is creation of organic acids like citric acid, oxalic acid, butyric, pyruvic, malic, different acids. And these acids and all these metabolites of these microorganisms and their activity, they are changing oxidation number of metals. Example is iron. iron have oxidation number 3, and you see this sand or minerals in this brown color. But this iron with oxidation number 3, when it's changed on oxidation number 2, this iron becomes liquid. So this iron is then back, is dissolved in this leachate, in this liquid residue, in this liquid fertilizer. And by changing of conditions, it can be recovered, precipitated back. Or, as I mentioned, in our case, it's beneficial if it's even stay inside. So depends, but it's possible. And yeah, so this is different between heterotrophic and autotrophic leaching in this source of energy and their food, actually, what these bacteria need for their life. And here you see also combination because the sulfide minerals are usually bounded in silicates. So it's hard for these autotrophic bacteria or even this sulfuric acid leaching or cyanide leaching to get into the sulfide minerals. But with our heterotrophic bacteria, we are creating corrosive holes. By this corrosive holes, we are releasing or making bigger surface also of these sulfide minerals. And you see it in this scanning electron microscopy picture. And there is also creation of secondary minerals. Here is acanthite, for example. And yes, I wanted to say this, that in many countries, they already ban usage of sulfuric acid and cyanide, because in most of, everywhere, in every mining operation in the world, they are usually using sulfuric acid or this cyanide leaching method, which are really very dangerous, as I already showed these pictures, what's happening then. And yeah, for example, in Macedonia, they already stopped everything, and they restricted new mining, which plan to do mining by these dangerous mining techniques. Another example, I will continue from these primary raw materials into secondary raw materials, which is waste. Here you see operation on copper tailings in the frame of rescue project. This waste is in amount 8 million tons. It's highly toxic, and it's making contamination 40 kilometers away. People in the area, all of them having cancer because of this, because they are living in this area, they are making they are having some crops there, they are drinking this water, and yeah, heavy metals are accumulating in the body. They will never disappear from your body, and they are just accumulating there, and then there is high risk of many diseases and cancer and Parkinson, Alzheimer, whatever. But this waste can be processed. This waste can be easily processed by our ecological technology. We are creating copper concentrate out of it, and this is a new source of copper for copper smelters, and also the residue will be used by ZAC and developed for construction products. So all this waste will be processed, and yeah, we will solve this environmental hazard. Another example is in iron ore mine tailings, which are produced in huge amounts all over the world. Iron is mostly for steel production, and we know that we need a lot of steel, so we need to do a lot of iron mining. But this mining produces again waste. And there was a lot of, again, accidents in Brazil. There was some accident with tailing pond, and also a lot of villages was under this waste. But on the other hand, there is again this demand for raw materials. So what we can do? We can this waste separate on iron, which can go back for or additionally for the steel production. Yeah, this is even in price €70 per ton. And at the same time, we are cleaning, we are separating this iron away and creating pure silica sand. I cannot mention exactly the name of this customer, but this country where we are working on, it's fifth in the world, which depending on import, and is fifth in consumption of silica sand because of also oil industry, because there is need for fracking sand, and this have to be high quality silica sand, and they have to import it more than 1,000 kilometers. And they're paying huge transport costs and really high price for this silica. But this silica can be delivered from this waste, which is produced in huge quantities in this country. Another example, this is from Europe, this is from Austria, where are tailings, which contain rare earth elements, which we can yes, recover, and another metals where there are all these metals removed. This residue is even usable for glass industry. And next example, what we do with this technology is soil bioremediation. Because in many cases, I think more than 6% of all soil in Europe is contaminated. And because of mining or industrial activities, it contain heavy metals and organic contamination. Also, this organic contamination, it's really in every country. There are minimally around 100 localities which are contaminated. But there is not much solution how to solve this problem. But as we can extract metals and even creating fertilizer which will really support this soil and make this soil fertile, we have solution how to remove these heavy metals and even improve the soil properties. And if there is organic, like oil or phenols, whatever, polyaromatic hydrocarbons, this is food for bacteria because they need organic source, and this is organic. So that's why this organic contamination is totally degraded on water, CO2, and non-hazardous substances. So that's how it's possible to solve these hazards. Okay, so we offer, this is our service, we offer also fast on-site measurements of metals. We are offering it for local municipalities, for people which wants to check their soil, if it's okay, if it's safe. Also, we measure tailings. We offer it for deposit owners, for mining companies. And then when we know chemical composition and what we want to extract, we offer or we supply specific bacterial consortia. For every specific input material, we have different ones. Then we do small-scale tests to prove efficiency and time of treatment. And then we go to big operations. Markets we are currently targeting is industrial raw materials, which I mentioned. This is our beachhead market, where there is potentially more than 100 silica sand deposits with many million tons of material which is wasted every year for these low value purposes like construction. All this silica sand is going mostly just to construction industry. And we can increase the value and create new markets for this material, like glass, paintings, coatings industry, this fracking sand, these many different applications where it have high value. And on the other hand, there is industrial wastes like used foundry sand, which is contaminated by metals and also organic from this casting process, casting of metals. And this sand is black, it's already burnt, but it's still very strong and it's good for construction. But it cannot be used in construction because of these contaminants. So currently this sand is deposited on high cost, up to 80 euro per ton. And it's produced in huge quantities, in millions of tons. So we can clean this material and create value out of it. Instead of this negative minus 80 euro per ton, this material have already value 10 euro per ton and can be used in construction products. Then we are targeting also contaminated soil, which is currently deposited even on 200 euro per ton price, and we then can use it, again create value even out of it, and create material suitable for liquid soil, which is used for filling of underground. This is again such new technology where we are cooperating with one German company. And also with one company from Denmark, one recycling company, which they are building these green walls near highways then from this soil, which will be clean after our process. So it's safe to use it again. And then last market we are targeting are mine tailings. As I mentioned, copper tailings, iron ore tailings, and different tailings, which are currently just deposited, so they have no value, they are just hazard for our environment. But we can create high value out of it, like iron, 70 euro per ton, or copper, 5,000 euro per ton. Zinc, it's also something like 4,000-5,000 euro per ton. And high purity silica sand, up to 150 euro per ton in this case. And then I will try to finalize it by impact. Impact of bioleaching on raw material value chain. It's starting in open pit mines. As I mentioned, this example, Rosia, Montana open pit mine, but this can be used in every mine where they are mining primary metallic raw materials and replace dangerous mining method. Then it's having impact on processing of raw materials. They do not have to use for processing of industrial minerals flotation and and acid leaching, how they are using these dangerous mining techniques can be replaced. And then we are having huge effect on transport of raw materials, which is needed because we want to create local resources. And we can create these local resources because we are having green technology, which can be accepted by society. People will be not scared from mining anymore if mining process will create even organic biofertilizer for the local agriculture. So if we will do nothing hazardous, there is high potential that we can get permission for many places where we can operate and create local resources and prevent wasting of raw materials. And in the end, we have huge impact on tailing dams and different wastes because we are doing recycling by this technology and returning these wastes into raw materials cycle. Okay, and I will finish with impact on society, environment, and economical impact which we have. So people will have safe food and safe water and healthy environment. then impact on our environment will be because of this green mining. So this mining will have no any more negative impact, and also we will have no toxicity in the environment, and also on contaminated, which is already contaminated, like soils, we can clean again. And also because of this new alternative for agriculture, we can have strong crops and really replace these hazardous chemicals in agriculture. So that will mean economical impact for deposit owners, that they will have high revenue, much higher than they had till now, because they will not waste their material, but they will have high application for their material and high value. For farmers, that means local, cheap, bio-organic alternative to their chemical fertilizers and pesticides. And for manufacturers, they will have local raw material sources, which means secure supply, and means also not high transportation costs. So that's probably it. Thank you very much for your attention, and I am very happy that I could tell you and introduce you Bioleaching. Actually, this new way of bioleaching, because as I mentioned, there are more ways how to do bioleaching. So hope it was clear, and if you will have some questions, yeah, I will look forward more on your questions, and I will be happy to answer them. So again, thank you very much for your attention.